Hi, so you hear me well? Yeah, I think so. So this is a paper I'm going to present. It was published at the last year PLDI, but unfortunately none of the authors were able to attend, but hopefully this year we're here. It's going to be about synchronization communication for Kotlin coroutines. And when you manipulate coroutines, so coroutines are kind of lightweight threads. So they're relatively cheap to suspend and resume. And unlike threads, they quite often get cancelled. Because when you manipulate threads, you almost never interrupt them because they're too expensive. You try not to suspend them because it's also expensive. But coroutines are run on native threads, so you can have millions of coroutines, but they are cheap to suspend and resume, and they can be cancelled. But that means that when you design synchronization for them, then you want this synchronization to be fair, because that's usually what the users expect from the synchronization. And with the costs of suspension and resumption being cheaper, it's more reasonable to provide fair synchronization because it doesn't affect performance significantly. And you also need to support cancellation efficiently. So that are the requirements we have. And when you take a look at coroutines, first of all, to share some data to synchronize the logic, you have the following primitives. You have a bunch of different channels to transfer the data. But besides that, you also need to have the standard classic synchronization constructs, such as mutex, such as semaphore, such as a read-write log. Or probably you also need countdown ledge barriers, blocking queues. So all the classic constructs that you use with the threads, you likely need for coroutines as well. And for channels, we have a special algorithm. We have a paper about that. And here we focus on the synchronization primitives. So here's the question: how to implement them in fair and abortable way. And here is the paper we published the last year PLDI, which introduces the cancelable queue synchronizer framework that allows you to easily implement all these primitives. But let's start with something simple: mutex. I think everyone knows here what mutex is. And let's try to implement it. Let's try to write some high-level, straightforward implementation. What I would do is to have a state field in this mutex, which is initially unlocked. And then you can change it to the locked one to acquire the lock. And by decrementing it again, you actually increase the number of waiting lock requests on this mutex. And to acquire the lock, we can atomically decrement this state. And if it was in the locked one, so you just acquired the mutex, you finish. And otherwise, you need to suspend and wait for the lock permit. So here we acquire the lock first, or increment the number of waiters, and we finish with the lock has been acquired, or suspend. And to release the lock, we do the opposite thing. We increment the state, and if there was, if it was in the locked state, we move the state to the unlocked one, so from 0 to 1. Otherwise, there is a waiting lock request that we need to resume. So in this case, we call special resume function that resumes the first waiting lock request. So these suspend and resume calls, they should maintain a queue of awaiting requests, processing this queue in the first in, first out order. And it's also possible that resume here can be called before suspend, because we can, for example, when acquiring the lock, first increment the counter, but before calling suspend, we can call unlock, which calls resume, because it notices that there is a waiting lock request. So it's possible to call resume before suspend. Similarly to the park and unpark semantics with the native threads, it's possible to call park before unpark and then, to call unpark before park. And in this case, when you call park, it shouldn't suspend. Here the same. When we call resume and then suspend, then this suspend call should just grab the permit and finish without actual suspension. And that's how we can implement these suspension and resume calls. The high-level idea is to have an infinite array and 2 positioning counters for suspend and resume operations. And similar to the modern queues, we start with incrementing the corresponding counter, thus reserving the slot for the operation. So suspend increments the counter, reserves the slot, and then it tries to suspend in the reserved array slot. So for that, it atomically replaces null with the reference to the current coroutine. Resume, on the other hand, it goes to the cell and tries to resume a coroutine that is there, putting the resume token. But if there is no coroutine, if a resume came before suspend, then it just puts the resume token and finishes. And in this case, when suspend comes, it notices that it should already be resumed and doesn't suspend. So let's take a look how it works. So we, for example, we start with the suspend. So we increment the index. We install our coroutine. So that's how I illustrated here. We install it into the first cell, and then we suspend there. And to resume, we increment the resume index. We go to the cell. We notice that there is a coroutine suspended in the cell, so we resume it. So we replace its reference with the resumed one, and then we resume the coroutine. So it gets resumed, and this suspend can finish, and we can also finish. But if resume comes first, then resume acquires the slot, goes to the cell, but it finds no one in the cell, so it puts the resumed token there, and it finishes because there is no one to be resumed. And when suspend comes, it goes to the same cell. It notices that there is already resumed token, so it does suspend. It already knows, aha, I was resumed because resume call came earlier, and we suspend. So that's more or less how these suspend and resume are implemented. And of course, in the actual implementation, we need to care about a lot of different things like cancellation. So when we are waiting in the cell, the coroutine can get cancelled. We need to carefully remove it from this slot. We need to update the state as well. But these are the technicalities. So the high-level design is that simple. And that's how we can implement the suspend and resume calls. We just showed how to use them to implement mutex. But let's say, OK, we don't want to implement mutex. We want to implement semaphore. Oh, sorry, it should be semaphore instead of mutex here. And semaphore is kind of a generalization for the mutex, which allows k threads to be in the critical section. So nothing is different from the mutex implementation. In this case, we just initialize the state with the number of permits, and the rest stays the same. And to measure the performance of this approach, we compared our mutex and semaphore implementations with the Java's implementations, because in Java they also have a framework for designing synchronization primitives. It's called abstract queued synchronizer. And here are the graphs. And here we also, so for For the mutex, we also have the classic CLH and the MCS logs, and we also have here unfair implementations of an unfair implementation of the semaphore, and two variations of our CQS-based implementations. So what we see here is that we are on par with the classic logs with our implementation. And regarding the semaphore, of course, with the unfair version, which allows threads to be processed not in first in, first out order, but just in any order, which is cheaper, of course. We are slower than the unfair version, but the more permits we have here, the closer we are getting to the unfair version. But what is also interesting is that the fair version is significantly faster with the CQS framework rather than with the Java's framework, because the design of the queue is more scalable. So we use finch indents on the first path, and in Java they use campaign sets with the loops to retry the operation when the cast fails. So that's the reason. And of course, we can implement many synchronization primitives this way, like a barrier, for example. So in this example, we have the only remaining field and waits until all the parties come to the barrier point. To implement it, very simple. So we just decrement the count of the remaining parties, and if it was greater than 0, we suspend. Otherwise, all the parties have reached the barrier point, so we resume all the rest. So what we see here is that with the cancelable queue synchronizer framework, implementations of such constructs are very straightforward and also very efficient. So I think right now out of time, so we skip the performance graph. So just to trust me that we are faster than Java, and we can implement many different things with the framework. So in the paper, we present mutex, semaphore, countdown, ledge, barrier, and also blocking queues. And separately, we also implemented read-write mutex, also using the cancelable queue synchronizer framework. And the last thing that is important, that we also proved all these algorithms with the iris in Coq, and the proofs are modular, so you can reuse the proofs for these suspend and resume functions, and the proofs of the actual primitives are quite short. So that's it. I hope you enjoyed the talk, and you now just have some intuition on how it's implemented. Thank you.
All right, we have 5 minutes for questions.
Hi, thank you. Really good work and good talk. I enjoyed it. In your graph, something happened between 32 and 64 threads. Is that? Yeah, there's a big jump, or between 16 and 32. Is that due to the machine, or?
You mean here?
Yeah. What happened there?
So here it's a semaphore. Mm-hmm. So when we parameterize it with the 32 permits, and we have 32 all over threads, then we never suspend. And then after that, we actually need to suspend periodically. Gotcha. That's why the performance degrades.
Now I can see the same on all of it. Okay, thank you.
Hi, really interesting. On the CLH lock and MCS lock here, are you implementing every time you acquire, allocating every time you acquire to create the lock, or are you caching that across calls?
Good question. To be honest, I don't remember now, but I can check, find you later, and answer your question.
Cool, thank you.
Hi, thank you for the great talk. I was wondering if you could provide some information on what kind of architecture these tests were run on, because write and read barriers behave very differently on ARM versus x86. So I would like to know to put these performance metrics into context.
I think it was on x86.
Okay.
We tried to run it on ARM architectures, but the trends were similar.
Okay, okay. Good to know, thank you.
Any more questions? All right, let's thank our speaker again. Yeah, thank you.